In today's video, we're going to cover suggested homework problems for 1.2 for Calculus 1. Again, this is the Larson Calculus 11th edition problems. So let's look at number 1 first. Give a brief description of the meaning of the notation. Limit as x approaches 8 if f of x is equal to 25. That means it is on the graph of f of x as we approach 8, negative 8, I'm sorry, is that negative or positive? Zoom in here. So we approach 8 from both the left and the right. Values a little bit smaller than 8, values a little bit bigger than 8. The y values of those points are approaching a y value of 25. The point 825 may be on the graph, or there may be a hole in the graph at the point 825, but the behavior of the graph on the left and the right is the same and is approaching 825, whether 825 is defined or not. So there's your brief description of what that means. You need to say something about x approaching 8, both from the left and the right, and y approaching 25 for your conceptual description there. So identify 3 types of behavior associated with the non-existence of a limit and illustrate each. Okay, so the first one is going to be limit as x approaches c from the left does not equal limit as x approaches c from the right. And an example of that would be f of x equals absolute value of x divided by x, which looks like this, where the limit of f of x as x approaches 0 from the left is -1. The limit of f of x as x approaches 0 from the right is +1, and they don't match each other. All right, another situation would be limit as x approaches c, as x approaches c from the left of f of x is, or limit x approaches c from the right is unbounded. And I want them to be equal to each other so it doesn't violate condition 1. Same type of unbounded behavior. So let me just give you the example of f of x is equal to 1 over x squared as an example. It has a vertical asymptote at x equals 0, and it's going to be unbounded in the positive direction, increasing with that bound both from the left and from the right. We abbreviate that idea as the limit going to infinity, but we know infinity is an idea and not a number, so it can't be a finite number L. The limit does not exist if we don't approach that finite number. All right, and then the last thing is oscillating behavior. And the classic example of this is f of x is equal to, I think that's sine x over x. But we can't tell exactly what it's doing by examining the graph. We'll talk more about how to look at that later. But let's just look at the graph right now that we're talking about, that it is like this, and then it starts jumping around like crazy here, and it goes back to, and we can't tell exactly what it's doing there at 0. So That limit wouldn't exist because we can't squeeze in on the values from the left and the right and see what it's doing because it's just going up and down so fast. We can't say that it's approaching any finite number L there and see what it is. All right. It's good for that one. Our next question is question 5. So let's estimate numerically with the table here, and go ahead and use the table that's provided for me and fill it in using my calculator. So I'm going to have x minus 4 in my numerator divided by, and in my denominator, x squared minus 5x plus 4. Table settings, I want this to be on ask for my x values, for my independent. Go to my table, and I want to see what happens at 3.9. So I have 0.3448, and I have 3.99, 0.3344, so I'm getting a little smaller, and then 3.999 is 0.3334. So what happens from the right, 4.1 is 0.3226, 4.01, 0.3322, and then 4.001 is 0.3332. And so it appears that this is approaching 0.3 repeating, which is exactly 1/3. And we'll learn how to prove that with algebra in a little bit. So number 17. One down here, and here's some oscillating behavior. That's what I was trying to think of was sine of 1 over x. I said sine of x divided by x, and that was the wrong thing, but I was trying to think of sine of 1 over x. Cosine of 1 over x will do the same thing. So cosine of 1 over x, I want to make sure that x is in radians and not degrees here. Good, it is. And let's go ahead and try to evaluate this. So let's get close to 0 from the left. Let's make a table. Say we don't know what's happening at 0. So let's use -1/10, -1/100th, and -1,000th. Let's use 1/10, 100th, and 1,000th here. -1/10, be -0.839, -100th is positive 0.8623. So I've jumped from negative to positive, and then -1,000th is 0.0, I'm sorry, 0.5624. So I'm really not discerning any pattern here. Let's just see from the right. It's even, so it should have the same numbers. And so I'm going to say that the limit does not exist. Because of oscillating behavior. Okay. Let's look now at number 19. Let's again create a table of values here. So limit x approaches 4 of x squared minus 16 over x minus 4 would be simple enough to do the algebra here, but that's not how we're supposed to do this. I think you can see that x minus 4 is a factor in the top and would cancel out, and we would have a function that agrees everywhere other than at x minus at x equals 4, and we could find the limit that way. But let's approach 4 from the left and the right. So 3.9, 3.99, 3.999, 4.1, 4.01, 4.001. So 3.9 is 7.9. 3.99 is 7.99. 3.999 is 7.999. I think I'm closing in on 8 here. 4.1 is 8.1. 4.01 is 8.01. And 4.001 is 8.001. Say, I don't know, but I think the limit there appears to be 8. All right, same thing with limit as x approaches 1, x to the 4th minus 1 over x to the 6th minus 1. Let's come into our y equals x to the 4th minus 1 divided by parentheses x to the 6th minus 1. Let's make our chart. We don't know what's going to happen at 1. Let's go 0.9, 0.99, 0.999, 1.1, 1.01, 1.001. We have 0.9 is 0.734, 0.99 is 0.6733, 0.999 is 0.6673. Looks to me like it's closing in on 2/3. Let's verify that from the other side. 0.6015, 1, 0.66, 1.01 is 0.666. This appears to be closing in on 0.6 repeating, which is exactly 2/3. All right, that was 23. Let's go to number 25 now. Limit as x approaches -6 of root 10 minus x minus 4 over x plus 6. So I'm going to have y equals, and then the numerator is going to be the square root of 10 minus x, and that is minus 4, and then denominator is x plus 6. We're getting close to 6 from the left, -6 from the left and the right. So -6 goes in the middle here, -5.9, -5.99, -5.999. Sorry, those are the things to the right because they're bigger. 5.999, -5.99, -5.9. This would be -6.001, -6.01, -6.1. -6.1 is -0.125. -6.01 is -0.125. -6.001. Looking like this is a very good approximation here. -5.9. -0.125, -5.99, -5.999. I don't know exactly what the point is there, but this looks like it's approaching -0.125, which is a -1/8. Right? So now at number 29. Limit as x goes to 0, sine of 2x divided by x. Again, make sure you're in radian mode for this. So sine of 2x divided by x, and we don't know what happens at 0, -0.1, 0.01, -0.001, 0.001, 0.001, 0.1. Right? -0.1, -0.001, -0.01, 0.001, 0.01, 1.9867, 1.9999, 2, 1.9999, 0.999, 0.67. So it appears this is approaching 2. Let's look now at number 31. Limit as x goes to 0, 2 over x cubed, and let's talk about why this fails to exist. So create a table to explain why that fails to exist. So 0, negative 1,000, negative 100, negative 1/10, 1,000, 100, 1/10. All right. 2 divided by x to the 3rd power, and negative 1/10. We've got all the values there already. So this is negative 2,000, negative 2, 1, 2, 3, 4, 5, 6, negative 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 2, 1, 2, 3, 4, 5, 6 zeros. And this is 2,000. So we've got 2 different problems here. Unbounded behavior from the left and right. Different unbounded behavior, but limit as x approaches 0 from the left is going towards negative infinity, and limit as x is going to 0 from the right is going towards positive infinity. We also have different limits from the left and right. Okay, so it breaks a couple of the rules there. And then we're going to skip all the way to number 70 here to just answer one last conceptual question here about why it's important that the function is defined on an open interval containing C, except possibly at C, and why is this requirement necessary? So understand that a little bit more if you do the delta epsilon proof of a limit, but we have to be able to approach the point or the hole for any amount of error epsilon greater than 0, squeeze in on that neighborhood no matter how small it is, and draw a neighborhood around a delta neighborhood around x that can be arbitrarily small. So I need all those points around C to be there in any interval that is close to C, and I need all the points around f of C to be there within the defined amount of error. So let's see if I can draw that picture for you that you probably used in class, that maybe the point is there, maybe it's not. Here's where I think the limit L is, and I've got an epsilon neighborhood here, L plus epsilon and L minus epsilon. I choose that error, and then that tracks over here to a certain place that I can go, inverse function kind of back to the x value here. Then I'm going to call this C plus delta, and I'm going to call this one right here C minus delta, that there should be this delta neighborhood right here around the C value. And as I come in closer and closer to L with epsilon, I come in closer and closer to C with delta. So I need all the points that are around C to be defined so that I can choose an arbitrarily small epsilon to get closer and closer to this desired L for my limit to exist. The hole doesn't need to be there, but I need to approach that hole or that point from both the left and the right. So that's what's going on. The picture is not a proof, but it's just a conceptual question, so the picture is going to help. All right, next time we'll come back and talk about 1.3, see for the next video.